morning, everybody. So today I'm here to present to you some of the work that I've done as part of my PhD thesis and at the company Oerlikon AM. My PhD thesis is here at the Technical University of Munich, supervised by Professor Meyer at the Chair of Materials Engineering for Additive Manufacturing. And I'll be here to talk about basically the comparison between zirconium and titanium, so two different group 4 transition metal elements as grain refiners, specifically in an aluminum copper lithium alloy. So first, just some introductions, and then we'll get into the content. So I've introduced myself. I'm doing this PhD working inside of the R&D organization of Oerlikon with support from the Technical University here. And this project in general is a collaboration with Linde. And so we're working very closely with Linde. Most of the builds are conducted at Linde's facility in Ludwigshafen by Siegfried Baer. And just as a plug for him, he's also been conducting trials of this and other types of, say, new aluminum alloys with these grain refinement strategies under different gases. So like what Camille presented this morning, there's a lot of interesting effects on the spatter and process byproducts. But anyway, Oerlikon and my contribution to the project are mainly via modifying the compositions of alloys to make them printable in powder bed fusion. So I think we all know this very well. This is a micrograph of a 7075 alloy, aluminum, zinc, magnesium, showing the characteristic hot and cold cracking. As Giuseppe pointed out, different types of cracking mechanisms, but unprocessable alloys, mostly due to the wide solidification window. And so as I think all of us here in this room know, when you add zirconium or scandium or titanium to these alloys, we can get a high degree of grain refinement, and that instead of the alloying elements, whether it's zinc or copper or nickel, segregating to the large grain boundaries, and that alloying segregation at the end of solidification causing cracking, we can get a very refined grain structure and printed material free of cracks. And so in this case, we've blended elemental powders. So like our first presentation of this session. And so the contribution here that I'd like to share with you was about like the difference between blending and pre-alloying powders and sort of a strategy for tuning the compositions. So this is also sort of an introduction slide from CalFAD simulations. We can see this linear plot of the phase fraction of the zirconium containing aluminide precipitate, this Al3Zr, which causes grain refinement, is linear with the increasing composition of zirconium in the alloy, all other elements being held constant. So essentially what the CalFAD is telling us is that at equilibrium, there should be no zirconium in solid solution, and all of the zirconium should be specifically in this single phase. And so the real motivation for this work and what I'm here to share with you today, which hopefully can be helpful in sort of guiding some future alloy development and wider community, is answering this question of what is the minimum zirconium or titanium content that's needed to, first of all, stop cracking, and second of all, have varying degrees of refinement of the grain structure. And so we've done this sort of with I'd say it's a unique method that was mostly due to the feedstock powder that we had available to us in this project. So essentially we have two aluminum copper lithium powders that have different amounts of zirconium and otherwise the same amount of copper and the same amount of lithium. One of these pre-alloy powders, which you can see the micrographs here, having the powder contains micron scale Al3Zr precipitates already in the feedstock powder, and a similar powder with no zirconium whatsoever. So when we print when we try printing this material, of course it's full of cracks like the 2024 we saw in the morning. And this material with 1.8 weight % zirconium prints with a very fine grain structure. And so essentially what we've done is just blended them together in varying fractions. And always when you're blending powder, and then analyzing the microstructure, we have this question of, is any inhomogeneity that we see in the microstructure due to the alloy, or is it due to an inhomogeneity in the powder blend itself? Right, and so what I'm just trying to show here is a relatively large area cross-section imaged in EDS of the 50-50 powder. So this is half powder particles with no zirconium, half powder particles with 1.8 weight % zirconium, blended together for a 0.9 weight % final composition. And we can see essentially that due to the same relative density, same particle size distribution, just a short blending time, the zirconium containing particles are homogeneously distributed in the non-zirconium containing powder particles. And just to further show that we have let's say the length scale of which these powder particles are distributed is smaller than the size of the melt pools. And so we can see and assume that it's basically behaving as a fully pre-alloyed powder. So from these two powders, we can generate any varying composition of zirconium to try to match with the CalFAT simulations. So in this case, this is the 1.5 weight % dilution. And when we look at these relatively large areas by EDS, we can see it's quite stable. Zirconium is distributed throughout without any influence of the powder. And so essentially what we've done is looked at different step sizes, 0.3 to 1.8 in the 0.3 weight % increments of zirconium, to try to sort of experimentally define the amount of zirconium necessary to stop cracking, first of all. And I'd like to point out, I don't have a slide on this, but we've investigated a quite wide range of process parameters, but only, let's say, in the industrially relevant range. So, of course, we've seen from the literature that by scanning very slowly, for example, with the 2024 we saw in Giuseppe's presentation, scanning very slowly, even without grain refiners, we can still generate a crack-free microstructure. But if you want to actually build parts, you can't scan at 200 millimeters per second or 100 millimeters per second. So we're trying to look at, the around 1 to 2,000 millimeters per second, and ideally pushing to higher layer thicknesses, because from the industrial point of view, build productivity is, I hope you all saw Frank Palm's talk yesterday, build productivity is extremely important for actually adopting any sort of new alloy. And with increasing zirconium content, we can see an increasing hardness due to sort of two factors that are not quantitatively separated here. First of all, just a traditional Hall edge grain refinement effect, increasing the hardness, and also an increasing volume fraction of the zirconium-containing precipitates. And so there's two criteria that we wanted to look at here. So first of all, very importantly, when does cracking stop? And we can see between 0.6 and 0.9 weight % zirconium at all process parameter ranges investigated, this is where we see no cracking. And then second of all, we want to define where we switch from this bimodal grain structure, where you have domains of columnar and domains of equiaxed grains, into a fully equiaxed regime, because that has an impact on the isotropy of the mechanical properties. And when, from Oerlikon's point of view, when we've talked to potential users of high-strength aluminum alloys, they say we want isotropic material. We don't want to design around different tensile strengths in the build direction versus the transverse plane. And so with zirconium, we can see that it's between 1.5 and 1.8% where we have this gradual transition essentially into a fully equiaxed grain structure. And basically we can just link these experimentally observed values to the phase fraction of the aluminide at the liquidus temperature. So in this case, around 670 degrees Celsius. At 1.8 weight percent zirconium, that's where we get the fully equiaxed grains. That's around 2%. The total molar phase fraction is the aluminide precipitate. And at 0.9 weight percent, so around 1% molar fraction of the precipitate is where we can say that we can stop cracking. And so here is where we can compare the effect of zirconium versus titanium. And although the precipitates, so the Al3ZR and Al3 Ti, have a slightly different lattice parameter, and therefore theoretically should, say, nucleate the FCC grains at a different efficiency, we can pretty much see that from the experimental results at least, the same molar fraction of that precipitate is what is necessary to stop cracking and to fully refine the grain structure. So this is the figure from the previous slide, right, with the dilution blend, so a fully pre-alloyed powder. And in this case, we've just taken the aluminum copper lithium powder with no grain refiner added. And so we can see sort of columnar grains, even with 0.3 weight percent titanium added, and blended elemental spherical titanium particles in at the same weight percent increments. And essentially what we can see is this, at the same phase fraction, around 1 molar percent, we stop cracking. So titanium is at equivalent weight percentages, and titanium is a more potent grain refiner because it's just a lighter element, right? And so it's the same, the mechanism by which we're stopping the cracking and getting a fully equiaxed grain structure is this heterogeneous nucleation of the FCC grains. And that's based on the molar fraction or the volume fraction of that precipitate in the melt when the FCC starts to solidify. And so I can just share sort of some preliminary results that we have on the fully equiaxed zirconium containing alloy, so an aluminum copper lithium zirconium alloy. We've printed pencil bars. They were machined and tested. And so first of all, I'd like to point out the high porosity value, right? So these are only 99.2% dense, which, as we know in powder bed fusion, is bad, right? And what's interesting is that these process parameters were selected based on a process parameter mapping DOE that showed this set of process parameters having 99.8 99.8% density. And so we took that value based on essentially single two-dimensional cross sections. We applied those parameters to this kind of build job, just cylindrical tensile coupons. And what we observed after cutting sort of a witness cube and also some of the coupons themselves after testing was much lower density than what we've previously seen. And so that's an important thing to point out here. This is just kind of an example of the build-to-build reliability ought to be tested more frequently. I think in a lot of studies, we find a good process parameter set and then we go ahead and apply them. But that's not always going to lead to repeatable results in the long term, especially if you think about moving the parts around on the base plate. We know there's a large spatial effect in the different locations on the base plate. We can get different density values. Maybe that has to do with the gas flow more so than the laser optics. But I think it's important to repeat some of our DOEs and ensure that we can really reliably print with the density values. because I know we all want to publish papers here, and when we get a great density value, that's great and we can move on, but in terms of transferring this to other machines, transferring it to, say, production, we need to do more testing. But anyway, this fully grain refined alloy has essentially isotropic properties in terms of yield strength and elongation in both the Z, the build direction, and the transverse plane. And we're running out of time. Yeah. And like some of the alloys we saw yesterday, not much strain hardening. So this is something we're still investigating, I think having to do with the high concentration of the solute elements, or the alloying elements, in this case copper, being pushed to the grain boundaries on solidification. Kind of trapping dislocations and impeding the movement for strain hardening. I think I'm running out of time, but quickly, we've also done some heat treatment studies, and basically to try and find sort of a peak hardening condition, both with constant holding time and also isothermal heat treating. We've gone to a higher temperature regime, because of the effect of those aluminum-free zirconium precipitants, which we know from the literature and thermocalc are quite stable. And currently there's tensile testing underway. And I can say we're also applying sort of a similar concept to other alloy systems, and also DED, so different kind of processing technologies. Yeah, I think I just want to make one extra point here. Hopefully next year I will have a contribution on corrosion, because we've seen a lot of really nice work about how adding these grain refiners to titanium, to aluminum alloys can really improve the mechanical properties and the printability, but we don't have any good data in the literature about how that affects corrosion. And I think that's a really important topic in terms of pushing anything into application, because that's normally a very hard criteria. So, thank you, and yeah, open to any questions or discussions after this talk.
Thank you very much for